Okay, people, I think we're live. Okay, well, not really live because you're watching a recording, but whatever. So I'm in Wilder. Emily and BJ are with me. I just, decided to make a video on point because I feel like that we should learn about some battery calculations. Battery calculations are pretty simple. I don't think it's going to take me too long to make this little video. Hopefully not, because I don't want y'all to sit there for 30 minutes while y'all listen to my boring voice. So, first off, I want to show y'all a really cool website. It's called Battery University. And basically, my internet will go faster. So we're really only going to be focusing on lithium-ion batteries during this lesson. The calculations that we do can apply to most other batteries, but when we talk about charging and discharging and the maximum and minimum voltages, those change for what kind of batteries we use. Now, we use two different kinds of batteries in the shop. The main kind that we use is lithium polymers, which are very, very close to lithium ions. And the other kind that we use are lithium iron phosphate. Lithium iron phosphates have a lower voltage than the LiPos, but they're very reliable. Okay, well, the website's not loading, but that's the website. So y'all saw the website. Okay, good. Very, very nice. Okay, so let's say we have a battery here. Okay, so let me insert a battery. If I can figure out how to do it. Oh, draw. That's nice. Okay, so I have a battery here, and we're going to do all pouch cells because that seems to be pretty much what we do. Pouch cells. I want a red. Okay, I'll just go with the black box. Okay. You can keep the music going. I like the music. But the music is fine. The music is nice. Okay, so there's a battery. Okay, so we have a positive side and a negative side, which really doesn't want to be red. So maybe we can tell it to be red. And we'll tell this to be black. Yay! Okay, so we have a positive and a negative side. And basically with every battery, we have an internal resistance, a C rating, and a storage capacity. Now, inside a battery, you can kind of think of a battery, an ideal voltage source is basically a battery without internal resistance. But we have internal resistance inside every battery, and internal resistance causes what's called a voltage drop whenever a load or a charge is put across a battery. So let's start with parallel and series because that's simple and most of y'all probably know it. So if we take this battery and we take another battery, oops, and we connect them like so. Okay, if we probe the voltage right here, my drawing is so nice. I'm doing this from a touchpad, by the way. If we probe the voltage right here, then it will give us a voltage twice of one cell because we have two in series. Now, if we take the same batteries and we put them in parallel, okay, pretend I'm stacking these on top of each other. and we put them right here, and we were to discharge them, then we would have, so let's say I put a big fat wire across here with a really tiny resistor, okay? This battery would be able to discharge twice as much current in order to, twice as much current without damaging the batteries than a single battery, and it will also have twice the amount of capacity as a single battery. Okay, so that's parallel and series for you. I'm going to give you some more numbers. So a standard lithium-ion cell ranges in voltage, okay? So the voltage range for lithium-ion is 3.0 to 4.2. Now, in some very rare cases, you will find that lithium ions can go up to 4.35, but that is pretty rare. So just know that there are different ones out there, but it doesn't really happen, and we certainly don't do it. So if you see a cell that is under around like under 3 volts, that means that it's technically a bad cell. Sometimes they can be brought back to life, but they will not ever work the same. If a cell is brought down to like 2.8 and then it's brought back to life, it might work okay, but it will still have a drop in capacity. If a cell drops to 1 volt or less, you might as well just blow it up or not use it, because it's not usable at that point, unless you're literally just making a flashlight, in which case your flashlight might only last an hour. Okay, so that's the voltage range. Now I'll teach y'all about what a C rating means. So a C rating, there's 2 different ratings. C ratings are given for a battery. There's a charge C rating and a discharge C rating. So generally, the charge C rating for lithium ion is 1, generally. If you don't know the charge C rating for a battery, always assume it's 1, unless it is a really, really tiny battery, like for drones and stuff. If it's a really tiny battery, assume that it's half a C, but otherwise just assume it's 1 C. Now discharge C ratings actually change a lot. And make sure that you look at your battery data sheet before you discharge a very large amount from your batteries so you don't blow them up. I have seen discharge ratings anywhere from I've seen discharge ratings anywhere from 0.5, 0.5 C, all the way up to 30 C, and I am sure that it gets larger than 30 C. It might even go up to 50, 60 C. That's just, that's just the highest I've seen. 30 C is tremendous, enormous, by the way. Okay, so now what a C rating is you take the C rating and you multiply it by the capacity to get the amperage. It's pretty simple. So a capacity is in a rating of amp hours, and the C rating is in a unit of 1/hours, but that unit is never really put in there. So when you multiply amp hours by 1/hours, then you get amps. And then obviously, yeah, so you have your amperage. So for the go-kart batteries, for example, the go-kart batteries have a C rating of 15 C, okay? So then we multiply that by the capacity, which is 8 amp hours. So each battery can discharge a total of, well, actually, I guess I could do that in my head. So each battery could discharge a total of 120 amps. So I'll just make sure I did that right. Yeah. So now, when we connect those in parallel, which we actually have 6 in parallel, then we can multiply that by 6. And then that gives us the total amount that we can pull from the pack at once. 720. Now, this does not mean to go out and boost the cart up to 720 amps just because the batteries can do it. We have other limiting factors like the motor and motor controller that will blow up if you put 720 amps across it. But that's just to show what the batteries can do. If you are ever designing a battery pack for something, I would recommend making a pack that can handle about twice the maximum discharge rating. And the reason why is because you don't want to ever have to worry about your batteries heating up. Even if your batteries heat up like 10 degrees Celsius, they start to hurt themselves. And that's not that much. And now my computer's dying. Well, darn. I guess recording video takes battery. Where's my charger? Ah. Okay, so now that we've gone over what the C rating means, let's go over what it means to have a voltage drop or a voltage rise. You can have a voltage rise during charging. So, all right. So we have a battery here, but inside the battery, we assume that there is a little tiny resistance in our batteries. Okay. Now, our go-kart batteries are rated for around 1 milliohm. So you can imagine that's pretty darn small. Oh, pooey. Okay, I'll just leave it there. Can I erase that? Oh, cool. Okay. So that's around 1 milliohm. Okay. So I'm hoping that especially the electrical engineers knows what happens when you put a load across a resistor. So when you put a load across a resistor, a voltage is applied across the resistor. Okay, so so if we put a 12-volt battery across the resistor, then that resistor will measure 12 volts. Okay, but let's say that instead we have 2 resistors, because that would make more sense for our case. So let's erase that and put in 2 resistors. So we'll assume that this is our load resistor. I'm really bad at drawing with the trackpad. And then we'll assume that there is another resistor that resembles the internal resistance of our battery. Okay, it's really small because that's, it's really small. Okay, so our battery internal resistance is around 1 milliohm. Okay, so when you apply a voltage across these 2 resistors, they will require that they will have a voltage drop across the line for each resistor by following Chernoff's amperage law, I think. Yeah, current law, yes. I hate Wikipedia, I really do. I am not a Wikipedia fan. Okay, so this is Kirchhoff's voltage law, which basically says as current is applied across a resistor, a voltage is yeah. So the current in a loop is equal. It's a net zero all the time, and then if you know the current or not or something, you can figure out the voltage. Okay, whatever. Okay, yeah. So so using Kirchhoff's current law, or just by using intuition and voltage divider law, we can figure out what the voltage is across these two. So let's say the battery has a voltage of 100 volts. So let's say it's our go-kart. Okay, so we have 100 volts across our battery. All right. Now we are going to apply a load. So let's say we want our load to equal about 150 amps, which is probably a medium, maybe like 3/4 of what our go-kart can do. Our go-kart could do up to 300, but I really don't like to put it up there because that's pretty high. But okay, all right, okay, so it's half power. I'll admit that it's half power. So that means that we need the resistance, this resistor, we need that resistor to be So we need that resistor to be 0.666 ohms, so 666 milliohms. All right, so that's what that resistor is. Okay, now this one is 1 milliohm. Okay, so we have 150 amps flowing across it, which let's go ahead and make it an even 150 ohms by making this 665. Okay, so so then what happens is we have a voltage that is applied across this. So by using you know, V equals IR, then we do 150 times 0.001. So we have a 0.15 voltage drop across the entire battery. Okay, so yeah, so our final voltage is going to be just like 99.85. So when the cart is under load, it will drop the voltage just a little bit. So that's what voltage drop is, and it actually does the opposite when it charges. So that would, if you charge it at 150 amps, which I hope to God we don't, then it would raise by 0.15 volts. So yeah. Let me make sure I did that correctly. I was testing the cart just a minute ago, and I really felt like that is pretty accurate. I did not see a lot of voltage drop except on our one bad cell. And I was pulling maybe, I don't know, 40 amps maximum. And the voltage maybe dropped 0.01, 0.03, somewhere around there. So you can do that calculation if you want to, but that's about what I got. Now, so that's internal resistance. Let me think if there's anything else. Oh, yes. So I wanted to show the damage that would happen to batteries if they were connected in parallel without being balanced. So let's say we have a couple cells in series. I mean, in parallel. Actually, let's just take two cells in parallel, just to make it simple. Now let's say we get a brand stinking new cell from Melasta, okay? That brand new cell is probably going to be 3.7 volts. 3.7 volts is a nominal storage voltage, okay? Now let's say we've been running our card outside for a little while, and that's how we figured out we have a bad cell or module. So we decided to replace it, and the rest of the batteries are around 3.2 volts. Okay, now that's not a big difference. That's only a 0.5 voltage difference. Okay, just 0.5. I mean, we could even do something like 3.4. Okay, so that's like 0.3 volts different. Okay, that's not all that much. Okay, now let's do our little calculation. So let's take 1 milliohm, 0.001, and multiply it. Wait, nope. And take, yeah. So we'll take 0.3 and multiply it by 0.001, and that equals, oh, whoops, divide. Sorry, guys. Okay, divide. That equals 300 amps. So as soon as you connect those batteries, they're going to have 300 amps of flow across those terminals. Now that will happen until the voltage is even. So let's say, yeah. So if we look at a voltage discharge curve, of a lithium ion. So this is like a standard voltage discharge curve. So we can see the cell that we were sent from Melasta is probably around 80% capacity, and the cell that we are now putting in the cart is probably around I don't know, 15% capacity. So when you connect those two together, you have like a large amount of capacity that you're dumping from one cell into the other, and it will destroy them, like just hands down. Even a 0.1 volt difference can still hurt the batteries. So that's 100 amps, which is still below the maximum, but that maximum is the peak maximum. So keep that in mind. Continuous maximum is around like 10 C. So even a 0.1 volt difference can still hurt the batteries. So what I would recommend for us to use is to actually use a battery balancer and balance the cells before we ever put them together. And then that way that we make sure that we don't hurt the batteries when we put them back into the go-kart packs. So I wanted to add one more thing onto here, just so everyone knows before we finish, because that's all the calculations. So so as you can see here, the heat builds around the cathode. I'm pretty sure it's the cathode, yes. So the heat builds around the cathode. Now, it's very interesting that it happens this way. It's mostly because of physics. The electrons are moving ever so slowly from the anode to the cathode. And as the electrons move, it actually pulls the heat towards the cathode. So that's kind of a little cool fact I wanted to add in there. So there's my little lesson on battery calculations. I hope I could help out. It's kind of fun learning about batteries. It's a whole nother ball game to get into the chemistries. But yeah, all right, well, y'all have a good day and do some fun stuff and don't blow yourselves up. Yay!